In this video, we're going to derive an expression for the divergence in an arbitrary coordinate system, orthogonal coordinate system. So the divergence is essentially a a measure of how much stuff is coming out of an infinitesimal point in our coordinate space, sometimes known as like a source. If you have some flux exiting a infinitesimal volume, you have a positive flux. If it's going into that little space, we've got a negative flux. So to calculate this flux, we're going to need to take a series of area integrals across each face of this little cube. Now we're going to use our metric again, so we have ds squared equals h1 dx1 squared plus h2 dx2 squared plus h3 dx3 squared. Again, these scale factors make sure that all of these components have a length scale. This ds is how far you've traveled along some arbitrary vector, and these are arbitrary direction components. So if you have a change in an angle, you need to multiply that by some factor to make sure that that change in angle corresponds to a change in length. So say we had an element where we've gone across some small angle d theta, multiplying by h1 will tell us how far we've gone along this distance here, or h2 or h3, whatever the scale factor is. Okay, so now we need to do a series of area integrals. I'm going to take the area integrals of the front and the back face, and in doing that we can sort of just commute the values and do the same thing with the side faces and the top and the bottom faces to give us a nice expression for our divergence. Now, so in taking this area integral, we're going to, given some vector function a, which exists on this orthogonal basis space, is a function of x1, x2, x3, and gives us a vector with components in the e1, e2, e3 direction. So we've got a1, e1 plus a2, e2 plus a3, e3. So we want to know how much stuff is going across this front surface. So we're going to take the surface integral of our function a across that little face dA, which is the front face. So we know that any part of that vector that's coming out of that front face is just going to be our A1 component vector, and that's going to be evaluated wherever this front face is. So that front face, we can say, is at x1 plus delta x1, and we're going to assume that because these distances are really tiny, we're just going to take a1 at x2 and x3, and this dA component is the direction of that front face, which happens to be dx1. And then we're going to integrate across that face. Now, because this face is such a tiny area, we're going to assume that the vector component a1 remains constant, and so we have a1 evaluated where we said it was evaluated before, multiplied by dx1 multiplied by the area of the face. Now the area of the face, we need to take into account these scale factors. So the area of that face is going to be h1 delta x2, h2 delta x2 multiplied by h3 delta x3. So put that in. x2 h3 delta x3. Now we need those h's there to make sure that we have the actual distance that we're traveling across the face of the square. We then are going to do that again for the back face. So we've got surface area of A dot dA dash. dA dash is going to be the back face, and so we're going to have the surface integral of now A1 evaluated at the back face, which is going to be just x1, x2, x3, given that we're only going a small distance in the x2 and the x3 directions. We can just sort of disregard them, and then the vector dA dash is going to be minus dx1 because it's pointing in the opposite direction. So again, we have to multiply it by the area of that back face, and we end up with a with a component minus, given this minus up there, a1 evaluated at x1, x2, x3, dx1 multiplied by the area, so that's h2 delta x2, h3 delta x3. Now we're going to add these components. So if I was to do components from the other two sides, I would, at the end, add them all together. I will just do the front and the back faces, and then we'll just sort of infer what the other faces would be. So I'm going to add together the front and the back faces. So the front face is A1, let's say it's h2 delta x2, h3 delta x3 dx1 from the direction, and a1 evaluated at x1 plus delta x1, x2, x3. I'll just make this a little bit smaller so I have enough room. and we're going to subtract from that h2 delta x2 h3 delta x3 dx1 a1 evaluated at x1 x2 x3. Now h2 and h3 are functions of x1, x2, and x3, and so need to be evaluated at those points. So we can actually group them with our a1. So we've got delta x2, delta x3 dx1 a1 h2 h3 a1 evaluated there minus delta x2 delta x3 dx1 a1 evaluated there. Now we can see that this is almost the definition of our partial derivative. So what we're going to do is we're going to multiply and divide by delta x1 so that we have something that because this dA here is a direction, we don't actually need this factor of dx1. It will come in a second. But we just want a1 in the direction of that dA. So we want a in the direction of dA, so that gave us a1 evaluated at that point. Then we needed to multiply by the area. So yeah, this just becomes a minus 1, and we don't need that, or that, or that. So now what we're going to do is multiply by, don't need that one. Now we're going to multiply by delta x1 and divide by delta x1 so that it looks more like the derivative, form that we're used to. So we're going to have delta x2 delta x3 delta x1 h2 h3 a1 evaluated at x1 plus delta x1 and x2 and x3, but we won't write that now just to save a bit of time. h2 h3 a1 evaluated at x1 and x2 x3, and we're going to divide by delta x1. Now this term here, as we let delta x1 approach an infinitesimal length dx1, that term there approaches the partial derivative. So we'll also let delta x2 and 3 approach dx2 and 3, and we'll end up with dx2 dx3 dx1 del h2 h3 a1 on del x1. Now that h2 and that h3 are inside that, as the scale factors will change as you move along your coordinate space. Now we can infer from this that the other sides will give us components dx1, dx2, dx3 del h1, h2, h1, h3, a2 on del x2 plus dx1, dx2, dx3 del h2, h1, a3 on del x3. Now we're almost there. We just now need to divide by the volume of the infinitesimal volume that we calculated it over, so that we have a measure of the divergence at every single singular point in space. So it's like a source per unit volume. And so to divide by the volume, we need to divide by h1 dx1, given that is the length of the volume along the x1 component, h2 dx2, the length across the x2 component, and h3 dx3, and multiply it by what we had there, and with some nice cancellation we'll end up with 1 on h1, h2, h3, del h1, h2, h3, a1 del x1 plus del h1, h2, h3, a2 del x2 plus del h2, h1, a3 del x3. And that is a scalar quantity, which is kind of like the amount of source per unit space. Thanks.